In the previous video, we talked about projection of an object along a subspace generated by a single vector or along a subspace of one dimension. Now we are talking about the projection onto a general subspace, let us suppose m dimensional. So let us see what is the structure. So let we have an x vector and the inner product space is V. So V is the vector space and the inner product is the dot product again. And let U be the subspace of m dimension and V is the subspace vector space of n dimension. And B is a matrix containing the basis vectors of vector space U or subspace U. So any vector in U can be represented uniquely by some b lambda. So this way, b lambda hat. So therefore, the projection of any vector x, this particular projection can also be written as the linear combination of basis vectors of U. So now to have the property that the projection and the original vector, the difference between these two vectors should be minimum, then the error vector must be orthogonal to the subspace U. So all the vectors of subspace U must be orthogonal to the vector generated by the difference of the original and the projected vector. There is another beauty in this orthogonality is that if you take projection along two orthogonal subspaces, two orthogonal complementary subspaces, then the resultant vector, the addition of the two projections, will give you the original vector. But in case if you do not take the orthogonal vectors, then it is quite possible that you will not get the vector just by adding the two vectors. So the best part is adding the projection in the complementary vector spaces, subspaces, orthogonally complementary subspaces. You can regenerate the vector by adding the two vectors. And this property we will utilize in the orthogonal decomposition of a matrix. We will see that shortly, but just first we will focus on this particular projection into a subspace of m dimensional. Okay. Now since we know that the projection, that is this, must be in the null space of basis vector or the subspace U. So all the vectors in the subspace U must be orthogonal to the error vector. So if that is so, we can say that B transpose this thing should come out to be 0, and ultimately we come up to the result that the desired scalar value is this one. So the desired lambda hat, it's not a scalar value, but it's a vector. It's a kind of a projection onto different basis vectors. So that is given by the coordinate of that particular projection. So lambda hat actually says the coordinates of projection in B or in U, in U, the subspace, coordinates of the projection in the subspace. So you get the coordinates of the projection in the subspace by this particular formula. Interestingly, B transpose B can have inverse. even if it is a rectangular B matrix is a rectangular matrix, even then B transpose B get the inverse if and only if we have linearly independent columns in B. So if all the columns of B are linearly independent, the B transpose B will be definitely invertible. And why it should be linearly independent? Because B's columns are nothing but the basis vectors of the subspace U. So they have to be linearly independent. And that's how the projection matrix comes out to be this one. Okay, this one. And now interestingly, you can find that if you take 2 times, if you find out the projection matrix multiplied by the projection matrix, you again get the same matrix. And why so? Because you are taking one's projection and then that projections is the same projection. You cannot now change this projection anymore. So that has this property. Sometimes what happens means where we use this kind of thing. So in general, what we say is this, that this is basically the least squares method of projecting the things onto the subspace where we can try to answer the things. So let us suppose we have certain data, we have certain features, and we don't know whether they are linearly dependent or independent, and we want to fit the data. And we don't know whether the features are linearly independent or not. In that case, we are not sure whether the basis vectors or the vectors that are going to define that particular value are linearly independent or not. In that case, we add this zitter term, epsilon I. Epsilon is a very small real positive quantity which is added to B transpose B, so that even if B does not have the linearly independent columns, even then you can find out the inverse of B transpose B epsilon I's inverse. So in that case, you can find out the inverse if you just add this small term. This small term is we say that it's a zitter term or a regularization term. Some people say it's a Tikhonov's regularization term. So this regularization terms helps us in inverting the B transpose B, even if B's columns are not linearly independent. In the next part, we are going to talk about this Gram-Schmidt decomposition of the matrix. The idea of this Gram-Schmidt factorization is based on this fact that if you take the projection of a vector into orthogonal complement subspaces, then adding those two projections will regenerate the vector. And that idea we are going to use in the Gram-Schmidt factorization of the matrix. In the next video, we are going to talk about Gram-Schmidt factorization. Thank you for now.